let us say some words about these three important inequalities. It's called the Schwarz, Poincare and Friedrichs inequalities. Let us start with the first of this, the Schwarz inequality, named after the famous mathematician Hermann Schwarz, which you see on this picture. Let capital V be a vector space with some scalar product called star. The Schwarz inequality tells us the following, that any vector x and y in this vector space has the following connected to this pair of vectors. We have the following inequality. The absolute value of the scalar product of x and y is less or equal to the norm of x multiplied with the norm of v. And here we recall what the definition of a norm is. This usual definition which we have shown you earlier. Let us give an example of the use of such inequality. If we let V, for example, be the vector, this vector space of all vector valued functions with n components, and we let omega as before be a subset of Rn, and we let lambda be a function, lambda here be a function which is strictly positive. That means that there exists some constant lambda minus and lambda plus, such that these inequalities is satisfied. Then we can define the scalar product between a vector function u and a vector function v in the following way. We just let it be this integral. And it's rather easy to show that this in fact is a scalar product. We have some rules for scalar product which we have shown you, and they are all satisfied. So according to this Schwarz inequality, which we are not going to prove, we have the following. We have, by replacing now in this inequality x and y with u and v, we obtain, by using this scalar product, the following inequality. So this is the Schwarz inequality in case then we have the scalar product defined in this way. So it's rather easy to see that this inequality is the same as the Schwarz inequality. One example is when lambda is just a constant 1, then we obtain this inequality. We are going to use these inequalities later on. Now we are going to consider the concept of Lipschitz continuous boundary. We are not going to go into detail here, but let's just show you what examples of Lipschitz continuous boundaries, or bounded subsets of Rn which are Lipschitz continuous. All these are examples of Lipschitz continuous boundaries, or subsets with Lipschitz continuous boundaries. What we can say is that if we have some sharp edges in the boundary, then these sharp edges has some angle. The angle is not zero. So any kind of polygonal surface could be or are Lipschitz continuous. A convex set is Lipschitz. Here we also have two examples of bounded domains with where the boundary is some polygonal surface. It's easier to understand the concept of Lipschitz continuous boundary by considering examples where the boundary is not Lipschitz continuous. Here are some examples. We may think that we have some very sharp edge here where the angle here is 0. So this is not a Lipschitz continuous boundary. Here is also one example. Maybe we could consider this as some circle here and some larger circle here, and they are connected in this point. So this gives angles which are 0. Here also an example of a not Lipschitz continuous boundary. The boundary is only touching in this point, and here the angle is also 0. We are not going to give you the precise definition of Lipschitz continuity, but because I think it's not within the scope of this elementary theory we are going to show you now. So I just want you to have an impression of what this means. Okay, now we are going to turn to the so-called Poincare inequality. And in order to understand Poincare inequality, we must have a picture of what Lipschitz continuous boundary means. So let omega be a domain, open bounded set with the Lipschitz continuous boundary, and the Poincare inequality holds. And the Poincare inequality tells the following: the integral of the square of the function u, which is a Sobolev function, should be less than some constant c0, and this constant c0 is only dependent of this space omega. So if we are given the space omega, this is some constant, and we multiply it with this guy. So this is the Poincare inequality. In this right hand side we have the integral of u, and we also have the integral of the gradient of u, the absolute value of the square of the gradient of u. And this inequality holds for the same constant, using the same constant for any function u in this Sobolev space w1, 2 of omega. Moreover, this constant c is strictly larger than 0, so it's a strictly positive constant. So this is the Poincare inequality. We also have some special inequality which only holds in the space of function, which is a subset of these functions, namely the function with 0 boundary conditions. And this inequality is called Friedrichs inequality, named after the mathematician Kurt Friedrichs. So we have this inequality is Friedrichs inequality, and it only holds in this W0 of 1, 2. So just to compare, this is the same inequality as this, except that we remove this term.